orbits. So we know in our solar system we have a few planets floating around the sun. It's amazing. We happen to be on one of those. And orbits are usually modeled as ellipses because that's the path they travel. However, to simplify the problem, we can use a circular path, right? So a little bit inaccurate, but good enough for a lot of use cases. So we know that the Earth orbits the sun in 1 year, which is that many seconds. And it has an average distance from the sun of about 150 million kilometers. Right, so we have a time and we have a radius. Part 1, calculate the speed of the Earth as it orbits the sun. Right, so in order to complete an orbit of the sun, the Earth needs to be moving with some velocity. And the hint is to use v equals d over t, but d is the circumference and t is the time period, so like 1 year. So let's do that now. So the distance the Earth travels in 1 year is 2 pi times the radius. Right, so here's the sun and the Earth, which is a distance 1 radius from the sun, will travel 1 circumference. So 2 times pi times 149.6 million, so times 10 to the 6. That's in kilometers, so we'll convert it to meters by timesing it by 1,000. So that's our distance. Now to work out the speed, it's distance over time, where we can compute the distance over time, where time is 1 year but in seconds. Yep, so let's compute that now. So 2 pi times 149.6 times 10 to the 6 times 1,000. So that's the numerator. I will divide by 3.155812 times 10 to the 7 to give almost 30,000 meters per second. Now looking at the values given, the radius has the least number of significant figures. It has 5. So we will round our answer to 5. So that would be 29,785 meters per second. So that is the speed at which the Earth orbits the sun. Alright, so as a vector, it would look something like that, tangential to its path. Okay, we got speed. What's next? Calculate the centripetal acceleration. So we know in a circular path, the velocity of Earth is actually changing. The magnitude is the same, but it's the direction that's changing. So in order to have a changing velocity, it must be accelerating. And it's actually accelerating inwards to the sun. Right? But every time, it just overshoots the sun, which is why it keeps the circular orbit. So centripetal acceleration is the tangential speed squared divided by the radius. And the radius was 149.6 million kilometers, so timesing that by 1,000. Right, speed squared, we worked out in part 1, divided by radius. So on my calculator, I have speed as the last answer, so I will just hit the squared button, and I will divide it by 149.6 times 10 to the 6. Actually, that would be times 10 to the 9 if I times it by 1,000, but let's just do it in full. Right, so that's right, yep. And we get 5.9302 meters per second squared. Yep, that's to 5 significant figures. And so that is the, times 10 to the negative 3. That is the centripetal acceleration. Now what's next? Calculate the centripetal force. I just realized we're missing a bit of information, aren't we? I'll update it on your question, but what are we missing? We are missing mass, because we know centripetal force is equal to mass times centripetal acceleration. So I'll put that in right now. Alright, we're back, and I found out the mass of the Earth as 5.972 times 10 to the power of 24 kgs. So let's use that. So centripetal force is that mass multiplied by the speed squared divided by the radius. Now we could do that calculation again, but we already worked that out. Right, was this answer here? So putting that in. And so that was our last answer, so we'll multiply that by the mass of the Earth, 5.972 times 10 to the power of 24, to give 3. How many sig figs do we want? So in this case, we're limited by the mass of the Earth, which is 4 significant figures. So we'll round our answer to 3.542. 42 times 10, what was it, to the power of 22? Yep. And what are the units for that? Newtons. Right, so even though the acceleration was very, very little, since the mass was so great, it's a planet, the force required to keep it in orbit is also very large. Okay, and now part 4, what fundamental force is providing this acceleration? Right, it is not called the centripetal force. That is a net force made up of actual forces. So have a think. What is pulling it inwards? Right. It will, of course, be the gravitational force. Yeah. That question was pretty easy. It just asked us what is the force, but we could, if you don't know it, this formula, Fg is the gravitational force, and it depends on the mass of the two objects. So in this case, the mass of the Sun and the mass of the Earth, and the distance between them squared. And this capital G is a constant, right? Newton's law of gravitation, no constant. So if you've never seen this formula before, definitely look up the gravitational force to get a bit more insight to it. Now, what was next? Another planet with some mass m orbits the Sun with a given speed and experiences a centripetal force of 2.1 times 10 to the 17 newtons. Write an expression for m in terms of r, the radius. And we were given the speed and the centripetal force. So looking at your data booklet, what relates M, R, V, and Fc? That would be the centripetal force equation, and it's asking us to rearrange for M. So rearranging for M, multiply by the radius, and divide by speed squared, like so. And in the question, we are given values for speed of 56 and centripetal force. So we can substitute those in. What was that? 2.1 times 10 to the 17. Yep, and 56 for speed. So we're technically done here, but we could simplify the coefficient, the numbers. So let's just put that in on our calculator. 2.1 times 10 to the 17 divided by 56 squared gives 6.7 times 10 to the 13. And it's that number times the radius. Cool. So we found an expression for M in terms of the radius, right? The distance of the planet from the sun. Now part 2, if the radius of this planet's orbit was twice that of Earth's, find the mass. So we were given the radius of Earth's orbit, so we can double it and then use our expression to find the mass. So the radius of this new planet is 2 times the Earth's orbit radius. That's a mouthful. Which was that, I believe? 149.6, yep, million, and then into meters. So let's compute that. 2 times 149.6 million times 1,000. 2.992 to the power of 992 times 10 to the power of 11. Cool, meters. So that is the new planet's orbit's radius. And we can finally work out its mass by using the expression that we found in the previous question. So timesing by the radius. So answer times, what was it, 6.7 times 10 to the power of 13. Now how should we round this one? So it'll be to 2 significant figures. So that would be 2.0 times 10 to the 25. Units would be kgs, right? Mass is in kgs, and since we used SI units for the other like inputs, our output will also be in SI units. How does that compare to Earth's mass? A little bit heavier, right? 1 order of magnitude heavier, times 10 to the 25 compared to times 10 to the 24, right? Does that make sense? So its speed is much slower. Okay, yeah. So have a reason about those proportions to make sure it makes sense to you. Otherwise, we're done here. I'm going to continue sitting on Earth, traveling approximately 30,000 meters per second, as you will be as well. See ya.